So the last speaker this afternoon is Huy Tuan Pham. Go ahead.
Thank you. So actually, quite a lot of my recent focus is on probabilistic combinatorics. So for instance, phenomena related to thresholds. This talk, we won't see probabilistic ideas appear explicitly, but in fact, they are still very important behind the picture. So with that, let me introduce the main character for today's talk, the set of subset sums. So given a set A of integers, the set of subset sums sigma of A is a set of all numbers that can be represented as a sum of finitely many distinct elements of A. We'll always assume that 0 is an element of the subset sum corresponding to the empty set. And of course, this definition would generalize immediately to any abelian groups. So for example, when A is a subset of Z to the D. Now, subset sums are actually a concept that's very simple and we are very familiar with it. So let's go through some examples that we all know. For example, if we take A to be the set of all powers of 2, we know that this is an additive basis. So in particular, the set of subset sums of A is all of the non-negative integers. And another example, simple example that I'll tell you is when you take A to be all of the integers between 0 and m, in this case, the set of subset sums is just going to be a longer interval around 0, and its length will be roughly quadratic in the size of A. Now, the set of subset sums is also related to other notions in additive combinatorics. So for example, the k-fold sumset, Ka, which consists of all of the possible sums of k elements from A, and the restricted k-fold sumset, which I'll denote sigma bracket k of A, and this consists of all sums of k distinct elements of A. Now, as I mentioned, subset sums is a fairly classical notion, so it is actually the subject of a number of old questions in additive number theory. So in the next few slides, I will just flash quickly through a few of these questions. Please don't pay attention to the detail. The goal is just to give you a glimpse of the flavor of some of these questions. They are mostly very natural and easy to state, but actually not so easy to prove. In this talk, I will only focus on one question at the end, which is about non-averaging sets. But of course, if you have picked your favorite among these earlier questions, then you are free to think about what the answer might look like in the next 10 minutes or so. But the first question is an old conjecture of Additive, and it just conjectures that any sufficiently dense infinite sequence of natural numbers must contain an infinite arithmetic progression among its subset sums. The next question is an extremal combinatorics flavor. So it asks for the largest subset of the interval from 1 to n, for which no subset sum is a perfect power, perfect case power. The next question is some Ramsey flavor to it. So in this case, we ask for the number of colors we need to color n-1, so that n cannot be written as a monochromatic subset sum. And now the most important question, which I will focus on in today's talk, is this old question of Additive and Strauss. It's about non-averaging set. So I said A is non-averaging if no element of A is equal to the average of a subset of A of size at least 2. And the question is about the largest size of such a set inside the interval from 1 to n. So before coming back to this motivating question in detail, let me next tell you some of the things that we know regarding structures in subset sums, and these will be important tools for us to come back to these questions. So actually, let me start again with some explicit examples that will hopefully give us some better idea about what subset sums tend to look like. Again, the first example is simple. You take an arithmetic progression starting at 0, and in this case, a set of subset sums will simply be a longer progression with the same common difference, and its length will now be roughly quadratic in the size of the set. The next example, let's go beyond the integer for a second. Let's look at the lattice ZD, and we can consider the set A, which is just the d-dimensional axis-aligned box where the side lengths are equal to m. In this case, it is a little bit harder to write out exactly what the set of subset sums looks like, but it is trivial to see that the set of subset sum is contained in a larger d-dimensional box, now with side length m times A. And with a little bit of thought, you can see that actually it contains inside it a translate of a d-dimensional box with side length only a constant factor smaller. So effectively, if you want to find things inside a set of subset sums of a d-dimensional box, then you can think about just finding something inside a d-dimensional box with a side length that is now of order m times A. Now we care about sets of integers, so a natural move to make here is just to take a linear projection from ZD to Z, and under this linear projection phi, if we are given a box, axis-aligned box B inside ZD, the image of this box is the so-called d-dimensional generalized arithmetic progression, or in short, a gap. And this is an object that is, it is a structure that is very important in additive combinatorics. And in particular, what we learn in this case is that the nice information we know about a subset sum of a d-dimensional box would also translate into very nice information that we know about a subset sum of a d-dimensional gap inside the integers. So just for example, the first picture that I draw here would just correspond to a two-dimensional gap, and this second line would correspond to what should a three-dimensional gap should look like. So now let me go to the master theorem. So it's the important structure result about subset sums. And because the talk is very short, please do not pay your attention to the detailed formal statement. Instead, I will just try to explain to you, at least intuitively, what the structure theorem is saying, so that at least you know the intuitive sense in which you should apply it. So roughly, what you can think about what the structure theorem is saying is that it is saying that if we are given any subset A of the interval n with size at least n to the delta, your delta is some arbitrary positive constant, then you can actually find, up to some small modification, you can actually find a very nice object, a generalized arithmetic progression P, which contains A, and for which you will obtain the conclusion that the set of subset sums of A behaves in a way that is fairly similar to the set of subset sums of P, which of course you understand very well. So to be a little bit more precise, what it is saying is that there is an additional parameter S, which is just slightly smaller than the size of A. And you can prove that you can find such a gap P containing A, for which the set of sums of S distinct elements of A, which is trivially contained inside the S-fold sum of the gap P, it also contains inside it a translate of now the CS-fold sum of P. So you'll only lose here an absolute constant factor. Now in picture, what you should imagine is happening is that you may have some set A sitting here in the integer, and the theorem is telling you that you can always find this gap, now two-dimensional, containing the set A, so that the behavior of the subset sum of A is closely captured by the behavior of the subset sum of this bigger and simpler gap. Now, there is another perspective in which you can look at the structure theorem, which will actually be useful for us today, and it's a little bit more geometric. So through this gap, P, in this case, it is two-dimensional, you can find an embedding of the set A into a higher dimensional lattice. So in this case, we embed the set A of integers inside a two-dimensional lattice. And the property that you have is that if you look at the image of A, which sits inside ZL, its set of subset sums or S-fold sums behaves in a very similar way to just the S-fold dilation of its convex hull. So in particular, this is very nice to us because effectively, through this result, we have been able to reduce a question about subset sums, which is in some sense complex and it has the arithmetic nature to it, to a question about studying the much more simple and amenable object, which is just dilation of convex body inside a higher dimensional space. Okay, so let me just now briefly remark that if you have time to look at this more closely later, it is in fact an essentially sharp inverse theorem for subset sums, and it is tight up to an absolute constant in the theorem statement. And this result and the framework around it is very useful. We see that it gives us very useful perspective and flexibility to handle subset sums. So we can actually use it to resolve a number of long-standing questions in additive number theory and also recover important previous results around subset sums. So with that, let me turn to the application that I want to tell you a little bit more about, and that is on non-averaging sets. So again, a non-averaging set is a set of integers in which no element can be written as the average of a subset of size at least 2. In other words, a non-averaging set is a set of integers that avoids solutions in distinct variables to all equations of the form kxk is equal to the sum of x0 up to xk minus 1 for any integer k at least 2. So in a sense, if you write it this way, then a non-averaging set is, in some sense, has some similarity to what is studied quite a lot in additive combinatorics, which are, for example, sets which avoid solutions to an equation of Roth type. So in particular, for example, sets that avoid non-trivial three-term arithmetic progressions. The only difference is that instead of avoiding solutions to one equation, here we are avoiding solution to all of these equations at once. Let me define Hn to be the maximum size of such a non-averaging set sitting inside the interval from 1 to n. So now our goal is to understand or to estimate this parameter Hn. Before going to the upper bound of Hn, which is the challenging direction, let me tell you a bit about the lower bound to this function Hn. And it comes from a very natural construction of Bosnet. So Bosnet shows that you can construct a non-averaging subset of n with size at least n to the 1/4. And his construction is in fact very simple. So what he does is he look at an appropriate two-dimensional grid. In this grid, he takes a set of points that lies in convex position. So for example, you take a discrete parabola inside this grid in 2 dimensions. This set of points, because they are in convex position, they are automatically non-averaging. So now all that you need to do is to find an appropriate projection from this 2-dimensional picture back to the integer axis, for which you can retain the non-averaging property. And if you do it carefully, then you can get this bound of n to the 1/4. Now, this construction, as you can see, is actually just an instance of constructions that are based on convex geometric structures. And these are actually very typical in additive combinatorics. So for example, Barron's construction also goes through a very similar procedure. So now let me turn to the upper bound on non-averaging sets and the connection to subset sums. So it starts with the following very simple observation of Additive and Strauss. You have A that is a non-averaging set, then no matter how you partition A into A1, A2, and a single element little a, you must have that a set of sums of A1 minus A and A minus A2, they can only intersect in the trivial element, which is 0. So Additive and Strauss, in their work, they define the parameter Sn, which is the smallest, so that for any 2 subsets of the interval of size Sn, they must have a common non-zero subset sum. And in particular, this observation allows them to upper bound the size of non-averaging sets by this parameter Sn, which is about subset sums. So then Additive with Sarkozy proved that this question on subset sums, the upper bound is square root n log n, which implies a similar bound for Hn. And then joint work with David Conlon and Jacob Fox, which in particular determines the sharp condition for finding large one-dimensional structures inside subset sums. We show that actually this parameter, this function Sn, the subset sum question, have order exactly theta of square root n. So now we run into a situation. Is the non-averaging set question similarly behaving to this function Sn, which is then giving us an answer about root n, or is it closer to the natural lower bound construction based on convex geometry, which gives us about n to the 1/4? So in the joint work with David and Jacob, which we introduced the structure theorem, we show that, well, actually we can use the structure theorem to break through the Sn barrier. So we can show a power improvement on the upper bound to Hn. And in upcoming work with Dima Zakharov, we proved that actually the maximum non-averaging set, Hn, is exactly n to the 1/4 plus lower order term. So in particular, the natural construction of Bosnet based on convex geometry is very close to being tight. So our proof relies crucially on the structure theorem and also the interplay between these structures and convexity. So roughly what happens is that we use the structure theorem to embed our set A into an appropriate higher dimensional lattice. Then we use the non-averaging property to show that this point set in higher dimension must lie in the proximate convex position. Then we turn to convex geometry and prove that if we have a set of points that is in nearly convex position in appropriate precise sense, then we can find density increment inside some smaller domain. So this allows us to then run a density increment strategy to prove the result. Okay, so in fact, we determine along the proof, we also determine the answer in any constant dimension D, at least 1. And let me remark that through the structure theorem, the proof exposes convexity quite explicitly, and it closely mirrors what you see in the tight example of Bosnet. And this is also, we believe, one of the first instances of a problem about sets avoiding linear configurations where you can really extract this convexity behind the picture. Okay, so in the next just 1 minute, I will just tell you that the structure theorem, in fact, it does have quite a lot more corollaries, and it allows us to get our hands on the subset sums really well. So for example, you can use it to determine kind of the optimal structure that you can find inside a set of subset sums, only knowing a lower bound on the size of A. And turns out the right structure is the so-called homogeneous d-dimensional gap. Don't worry too much about the detail. And I don't know if anyone has spent the time thinking about the other questions that we didn't pay attention to. Using the same structure theorem, we can determine the answer or close to the answer for many of them. So for example, this extremal question of Additive, or this Ramsey type question, in which it turns out that the answer looks like this. I don't know if someone figured it out in the last 10 minutes. And it's somewhat surprising that this structure theorem allows us to determine the answer fairly precisely, even for these Ramsey type questions. So I'll just end by saying that there should be still a lot more interesting things to learn and see, even in the polynomially dense regimes, where the regime where A has size at least n to the delta. And perhaps there are also interesting applications of structure theorems for subset sums in related applications in theoretical computer science. But the high dimension regime, so when your set A goes to size n to the little o of 1, seems to be particularly interesting because now the dimension dependence really starts to matter. And I also think it's interesting to say that the non-averaging set case is only the start of an investigation, and hopefully we can understand better the role of convexity for other arithmetic problems involving sets avoiding linear configurations as well. Thank you.
Okay, any question to Huy Tuan?
It struck me as natural, like one could also say like how many ways you could write something as a combination of, and it seems like that's not at all kind of thing that you're studying.
Right, so there are certainly lots of questions around a number of ways of representing certain numbers. For many of these subset sums question, I haven't seen that as much. They appear quite a lot when you look at sums of finitely many terms. So for example, how many ways you can write an element as a sum of k terms from a certain sequence where k now may be a fixed constant instead of growing with the size of A. But indeed, in what I have presented here, we were not really paying attention to this number of ways. And actually, I think because when we study subset sums in the regime that we study, things start to get to a fairly structured situation. I think there should be a fairly good way that at least we can get some handle on the number of ways of representing integers.
Okay.
Is it easy to describe, like what is your construction of your embedding into higher dimensions?
Yeah, if you have a gap, then it has a very natural embedding into a higher dimension. Just use the coordinate map. And well, the structure theorem embeds your set A as a subset of a gap. So it naturally gives you an embedding into the dimension of the gap.
What about sets which have no k-term arithmetic progressions or things like that? Are methods irrelevant, or it's completely different?
So right, so the method here, in fact, well, part of what it relies on is also the fact that we start to look at equations in more and more variables. So k is growing with the size of A. So when you go back to the regime where k is a constant, then probably what you should look at is not the methods that are developed here, but in other places. For example, the methods that go into studying Roth equation, x minus 2y plus z equals to 0.
More questions? Okay, so no more questions, and let's thank Huy Tuan again.